All right, so we can also look at curved isobars at the surface. These are always going to be at sea level. And we're going to take a look at them, recall, always in the Northern Hemisphere, because you guys are probably going to teach someday in the Northern Hemisphere. In America and in the Northern Hemisphere, most of our, or I should say all of our, big weather systems come from low pressure centers, like this diagram up here. So if we have like rotation happening, or a tornado, or a hurricane or something, we can predict which direction the wind is going to travel by our force balance winds diagram, which we can just overlay onto curved isobars. So the first thing that we have to do is recognize that our forces are still the same here, because we're still building the same force balance winds diagram. We have a low pressure center given to us. This could also be written in the form of values, like numbers, that we've been seeing on our force balance winds diagrams in the past. But today I just gave it to you. So our low pressure is in the center. We have to take into account that that means that there's high pressure everywhere else around this system. So our high is going to be out here. We're going to have high over here, because our pressures are relative to each other. So on our little air parcel that I've drawn in right here, the first thing that we can always add is our pressure gradient force. Again, like we've been doing, always traveling from the relative high to the relative low. The second thing we can always add is going to be our Coriolis force, which in the Northern Hemisphere pulls to the right from our pressure gradient force. Recall that we don't calculate the angle in this class. That's too much math for us. But we're going to go past 90. And there's our Coriolis. The wind should always end up being between the two in the Pac-Man mouth, like we've been practicing. And we can always add friction opposite the wind at sea level. So we can see already that our wind is going to travel this way from this air parcel. What happens if we were to do it on the other side of the air parcel? Perhaps in a little bit. Well, we can still put our pressure gradient force on first from our relative high out here towards our low in the center. We can still add our Coriolis force being pulled to the right at some angle past 90. And we can still put our wind in the little Pac-Man mouth and friction behind. So we can see that our winds are traveling in opposite directions on opposite sides of these curved isobars. This is going to give way to rotation and eventually mid-latitude cyclones that we'll talk about. So these are going to end up traveling in towards the center of that low to fill in the low with some of that high pressure. The Earth likes to maintain equilibrium, and this is just a rotational way of filling in that gap. So low pressure center systems, we call them cyclones. For our high pressure center systems, which aren't really systems, but we have them displayed on weather maps in the continental US and other places above continents. Again, our pressures are relative to each other. So we've got a high pressure in the center. We should be having low pressures relative to that on the outside. So we can start by putting our pressure gradient force in from the relative high out to the relative low. In the Northern Hemisphere, still, our pressure gradient, or our Coriolis force, is going to start at our PGF and twist off to the right at some angle past 90. And we can still put our wind in the Pac-Man mouth here and friction behind it. If we try that on the other side, perhaps in a little bit, we can still put our pressure gradient force going from our relative high to our relative low. We still have Coriolis being pulled to the right at some angle past 90. And we can still put our wind in the mouth and friction behind it. So we can see that our pattern is kind of opposite of what we have with a low pressure center system. And our winds are kind of trying to escape this area the same way they were trying to fill in our cyclone up here. They're trying to get out of the high pressure area. There's too much air in there and it needs to go fill those lows. So we're going to end up making rotation that's opposite of the cyclone above, and this is going to go out of this system. This air is going to go out and it's going to end up going clockwise. So these we call anticyclones. Marker's not working. For exam purposes, if you need a way to remember this quickly, cyclones goes with a low because they both have less letters in them. Anticyclone is paired with a relative high at the center, high having one extra letter than low, and cyclone has less letters than anticyclones. But we'll talk about that relationship in class more. So here we're traveling clockwise out. And in a cyclone system, we're traveling counterclockwise into the system. And that's how we make force balance winds on curved isobars.